So looking at the energy chapter, we're going to basically look at or focus on more of mechanical energy and also discuss the conservation of energy law, which is the most important law of nature. Energy, of course, is one of the most important quantities in nature. Nothing interesting really happens unless energy is converted from one type to another. However, the concept of energy is a little bit abstract in the sense that it's nothing that we can hold or touch, but yet to have an interesting process go forward, we need energy to be conserved, and the energy has to come from someplace and go someplace. The most important aspect of energy, of course, is the conservation of energy law. It states that the total energy in a closed system cannot be increased or decreased. Thus, energy cannot be created or destroyed. It is simply transformed from one form to another. So essentially, we always start out with so much total energy in some type of closed system. Now, we can have an open system where the energy is introduced from the outside, but as long as we're taking that into account, the energy is just not coming out of nowhere. So the total energy in the system really has to remain constant because energy just doesn't appear without it being extracted from some other region. So essentially, this gives us a finite amount of energy that we have to play with. And in many processes, we can track what's going on by simply seeing how much energy we're starting with, how much energy we are losing in one part of the system, and therefore know how much we're gaining in another part. Consider the conservation of energy in a car. Typically, an automobile is powered by an internal combustion engine. Now, for a car, this energy is introduced from the outside as chemical energy, usually in the form of gasoline or diesel, which will be combined with oxygen to release this chemical energy in the form of heat. So we start out with chemical energy, okay? That chemical energy goes through combustion, which means it reacts with oxygen. The chemical energy becomes heat as the results of the combustion form a hot gas. This hot gas, by PV equals nRT, increases its pressure. The pressure does work on the cylinders in the engine, and then the cylinders do work on the ground to propel the car forward. So again, if you trace the energy started as chemical energy in the form of gasoline, then was converted into heat, causing the gas to increase its pressure inside the cylinders. And then as they expanded, they did work on the rest of the system. But at no time was any energy lost. Whatever energy we started with in the form of the chemical energy was converted into all heat. We can see this is an infrared photo of a car and the hot exhaust coming out. Some of that thermal energy was lost to the outside. Some of it was turned into work. And again, this is responsible for propelling the car forward. Now, the SI units for energy are the joule. The joule is named after James Prescott Joule, who was able to demonstrate that you can convert gravitational energy into heat. Before Joule, basically there was a debate whether heat was a form of energy or whether heat was like electricity. Electricity is the flow of charged particles. The scientists of the time, some of them felt that heat was just the flow of an invisible substance like charge known as caloric. However, Joule was able to demonstrate that using gravitational energy from a system of pulleys, you could convert this into heat, and that the amount of heat would be proportional to the amount of gravitational energy used. And that showed a direct connection. Again, with conservation of energy, whatever energy we start out with, in this case in the form of weight suspended on these pulleys, had to be accounted for in the case of an increase in temperature in this bath right here. All right, so the joule is the SI unit for energy. We say that 1 joule is equal to 1 Newton times meter. And if we think about where this comes from, 1 joule comes from doing work on a block, okay? Block of mass, it doesn't have to be anything particular. We do work on that block, pushing it with a force of 1 Newton for a distance of 1 meter. 1 Newton meter gives us the joule. And again, another way of writing this would be that the joule is equal to 1 kilogram meter squared per second squared, whereas the Newton is kilogram meters per second squared. If we multiply that by a meter, we get back a kilogram meter squared per second squared. So that's the unit that we're going to be using throughout this chapter and throughout this semester. But it is important to note that there are other units of energy. The calorie is a very important unit of energy, still part of the metric system. SI units are all part of the metric system, so the joule is a metric unit. But the calorie is also a metric unit. Unlike the joule, which is based on mechanical energy, the calorie is based on thermal energy. And it is the amount of thermal energy needed to take 1 cubic centimeter of water, that's 1 milliliter of water, or 1 gram of water, and raise the temperature of this water by 1 degree Celsius, or 1 degrees Kelvin, more accurately. So again, another metric unit of energy. This, of course, is the calorie. To do a conversion between the two metric units, there isn't a nice, clean way of doing that. It's actually based on the specific heat of water, and we'll talk about that later on. But 1 calorie is equal to 4.16 joules. If we round that up, roughly 4.2 joules. So the calorie is a bigger unit of energy. Roughly, if we want to convert from joules to calories, we can multiply by 4.2. If we want to convert from joules back to calorie, we divide by 4.2. So for instance, 20 calories is about 84 joules. 20 times 4.2 is 84. And 50 joules is 12 calories. 50 divided by 4.2 equals 12. Now, food calories are actually something different from regular metric calories. Many times we'll call the regular metric calorie the small c calorie, because when you write it, we write it with a small c al. Food calories are written with a large C, capital C, al. And they're actually 1,000 times greater than the metric calorie. Now, this is done in the United States, and it's very confusing because the big C calorie is 1,000 times greater than the small c calorie. However, if you go outside the United States, they use the more proper term, or they use the more proper designation, kcal. Okay, so 1 kcal is equal to 1,000 calories. Let's take a look at this nutrition facts label. This is a little bit of an older one. The newer ones really aren't that much different. If we look at this, it shows 250 total calories. Now, human beings, being biological creatures, get their energy basically from their food source. Okay, animals, of course, will eat plants and other animals to extract chemical energy from them. Plants can generate their own chemical energy using photosynthesis, but we're really left to digest the chemical energy that we need to run our bodies. If we think about this, 250 food calories, let me go back to the pen, 250 food calories is actually 250 kcals, so 250,000 calories, okay, metric calories. If we multiply that by 4.2, we get more than 1 million joules, okay? Or roughly a little bit more than a megajoule of energy. So 250 calories doesn't really sound like a lot. I think the normal human being needs, about 2,000 calories just to get enough energy. So you're not, spending more energy than you're consuming. So, at 250 calories, 1 megajoule is quite a bit of energy. Now, another unit of energy that we come across commonly is a kilowatt hour. And the kilowatt hour actually is derived from a unit that we're going to talk about later, and that's the watt. The kilowatt hour is using 1 kilowatt of power for an entire hour, okay? And later on, we'll see that the watt is equal to the number of joules per second. So if we multiply that by hours, and we know there's 3,600 seconds per hour, okay? The kilowatt hour represents using up 1,000 watts, 1 kilowatt, over 3,600 seconds. 1,000 times 3,600 gives us 3.6 million joules, or roughly the conversion is 1 kilowatt hour is equal to 3.6 megajoules, or 3.6 million joules. All right. This is a power bill. This is a bill from the electrical company, and they charge you according to how much energy that you use. As you can see right here, we have on the vertical axis the amount of kilowatt hours used every month listed, and it looks like they use roughly a maximum of 780 kilowatt hours. That's in January, and then they use much less in August. Drops down, probably around 400, about 400 megajoules. So again, the meter on the side of your house, your apartment, where you live, monitors how much electrical energy you consume within your household. At the end of each month, the power company comes and reads the meter, either directly or electronically, and then converts that to a bill. You have the number of kilowatt hours that you use, and then they multiply it by the rate for that particular amount of energy. Oops, let me erase that. Electric vehicles are becoming more and more common. Here are 2 electric vehicles that I've listed because we actually have additional information about them later on when we talk about energy efficiency. The first, the one on the bottom, is the Tesla Model 3. And this, unlike internal combustion engines, like gasoline cars and diesel vehicles, stores its energy chemically within a battery rather than chemically within hydrocarbons. The Tesla Model 3 can store 54, 62, or 75 kilowatt hours of electricity in its battery, again, in the form of chemicals. They're actually lithium-ion batteries, and it's an electrochemical system. So what happens here is that the lithium ions will migrate from one side of the battery to another side of the battery, where they'll have more potential energy. And then as we allow them to migrate back, we can extract useful energy out of that. Here's another electric vehicle. This one's rated at 66 kilowatt hours. And again, that's fairly typical for vehicles that can go over 200 miles. We will compare these vehicles again to internal combustion engines when we compare how energy efficient different modes of transportation are. Just to do a conversion, if you want to calculate for the Chevy Bolt how much energy that is, 66 kilowatt hours. If we convert that to joules, that's 2.4 times 10 to the 8 joules, or 240 megajoules. With the Tesla, the highest capacity is 75 kilowatt hours. That is 2.7 times 10 to the 8 joules, or 270 megajoules. Again, this seems like an incredible amount of energy. However, if we consider this to an internal combustion engine, such as a gasoline engine, gasoline contains 127 megajoules per gallon. So essentially, when you compare apples to apples, for the same amount of energy that's contained in 2 gallons of gasoline, you can power one of these two cars or fully charge them. And both vehicles have a mileage of over 200 miles. So typically when they rate the fuel efficiency of these cars, they give you an equivalent miles per gallon, and both of these are well over 100 mile per gallon equivalents. Another unit of energy that we also use in everyday life is the BTU. We typically say BTU, but technically it's BTU per hour. You see like a furnace talking about how many BTUs, or a air conditioner talking about so many BTUs. They're actually referring to how much energy, in the case of the furnace, that it can extract from the chemicals that it's burning and convert that into heat and dump that into the house. The air conditioner is using this to talk about how much thermal energy, heat for instance, it can take from within the house and push to the outside. So again, with furnaces and with air conditioners, we still tend to use the US customary unit, which is the British thermal unit. But again, in science, we do like to use joules. Okay, so there are many different types of energy. And again, for processes that are really interesting, energy is converted from one form to another. We've already seen how chemical energy is used for a number of different purposes. For chemical energy, we use chemical energies to make cars go, chemical energy within our bodies, power all the different systems that we have going on, keeps our heart beating, keeps our diaphragm moving so we can breathe. It makes our muscles move. Basically, the chemical energy that's being stored here comes from the food that we use. Some of the mechanical energy is turned into heat. This is true for both the car engine. It's true for our bodies. Most of the energy actually leaves in the form of heat. And again, chemical energy can be used in power plants to create electromagnetic energy. Electromagnetic energy in the sun can be used to be converted into electricity. Nuclear energy can be used to create electricity. So there are many different types of energy that we see in nature. But again, most of the processes that we come across are simply a conversion of one type of energy into another type of energy, always with the conservation of energy law. Let's look at mechanical energy. Now, the word mechanical talks about motion. Talk about mechanical, we're usually relating two different things. We're relating a force, and forces are responsible for changing motion, and movement or motion. So mechanical energy is the energy that changes the motion of an object or is involved with the actual motion of an object. All right. Three different types of mechanical energy. First type of work is work. Work is mechanical energy that is added or removed from a system. The next type is kinetic energy. That is the actual energy of motion. The last type is potential energy. This is energy that is stored and can do work in the future or be converted directly into kinetic energy. Let's start out with work. In many cases, we can reduce work as simply the force pushing on an object or pulling on an object times the distance that the object moves. So oftentimes you'll see work is written as this equation right here. We have to be careful with that. For this case, both the force and the displacement or the distance that the direction that the object is traveling are one of the same, okay? When the force is constant, when the direction of travel is the same as the force, we can use the equation work equals force times distance, okay? Now, unfortunately, this equation has a little bit of a problem, okay? When it converted this, when it converted this symbol right here was supposed to be a delta. And again, if we look at this, simply saying that the work, W, is equal to the force, here's F, times the distance or the displacement, that's delta X, and here's delta X right here. So I want to calculate the work that a particular force F will do on a box as it moves from one location to the other. Okay, again, very, very simple. We ask ourselves, what is the force in the direction that the box is traveling, and how far does the box go with that force on it? Think about different sporting events. Shot put, javelin. We're trying to get a projectile to go some distance. Now, in throwing the shot put, we want to place a force on the shot put, but we don't just simply release it instantly after the force is applied. If you've ever seen the shot put thrown or the discus thrown, the athlete actually has almost sort of a wind-up. They sort of rotate their body around a central axis. And they do this because they want to maximize the amount of distance that the projectile travels before they stop putting a force on it, okay? Sort of have this spiral-like motion that as they unwind, they force the projectile faster and faster and then release it, typically launching it at about a 45-degree angle. It's also true with the javelin. The person throwing the javelin runs down a track, runs down a path, going to the foul line, they release it. And again, they're placing a force on this javelin, getting it going faster and faster till the time that it's released. So what I'm saying here is what they're trying to do is, yes, you've got to be strong. You've got to be able to place a large force on it. But you also have to use technique where you maximize the distance that this projectile travels while it's still under the influence of the force. So technique is very, very important in maximizing the energy you put into the projectile. Also true for baseball and softball. If you ever watch a pitcher throw a baseball, or you pitched in baseball or softball, you know that the ball actually travels some distance while it's in the hands of the pitcher before it's actually released. Same thing for softball. It's pitched underhand, but the softball traces almost a windmill-like trajectory while it's being forced before it's released. Again, the longer this distance that's being pushed by the pitcher, the more energy that can be transferred to it, and the more effective the pitch is, depending on if this energy goes into maximizing the translational speed or the rotational speed. So again, work doesn't happen by itself. Think about it, where does the work come from? Well, again, one of the easiest sources of work, the source of the energy, is chemical energy. In the case of an internal combustion engine, that chemical energy is turned into thermal energy. That thermal energy becomes work that makes the car go forward. Let's do a quick calculation for work. Here we're doing work done by a car engine. We have a constant force of 250 newtons acting on the roadway due to the force provided by the engine itself. So 250 newtons, this is the force provided by the engine to overcome air friction, to overcome other friction. Generally, when we're just coasting, all the forces add up to be equal to zero. But again, if you ask how much work does the engine do, you take only the force from the engine. You then ask, all right, so 250 meters, how far does it go, displacement? And by taking the product of the two, 250 times 3,000, that's 750,000 joules, okay? Or 750 kilojoules. You want another conversion, we can even convert to megajoules. That's 0.75 megajoules. So again, car engine produces 250 newtons. Car travels 3,000 meters, okay? The product of the two give you 750,000. Now, there are cases where the force that's being applied to move something isn't necessarily in the same direction as the displacement is taking place. In this case, we have to use a trigonometric function we call cosine. So once again, it is the force in the direction of travel times the actual displacement during the travel that gives you the total work done by that force. Here, however, we have a force where some of it is pushing in the direction of travel, some of it is pushing perpendicularly to the direction of travel. So we only want the component in the direction of travel, and cosine allows us to get that. Okay. We don't do very much with trigonometry here, but you should understand that when I say the cosine of the angle, okay, we can express this angle either in degrees, which you're probably more familiar with, you're probably more comfortable with, or with radians. Now, if the angle between F and the direction that the displacement is in is zero, if they're both pointing in the same direction, then the cosine of 0 degrees, cosine 0, is equal to 1. So that means that in our equation, work equals force times cosine theta times delta x. The cosine theta is just equal to 1, and we get the maximum amount of work done. At 30 degrees, okay, put degrees there. At 30 degrees, cosine of 30 degrees is 0.87. Okay, 0.87. And that means that the maximum amount of work that we're going to get out of here is only 80%, 87% of the full potential that the force can transfer energy to that block. Cosine of 45 degrees is about 71%. I was going to say 77, 71%. Cosine of 60 degrees is 1/2. And if we go all the way to cosine 90 degrees, we do no work at all. When our vector for force is pointing straight up, right? There's no component of it in the direction of the displacement. Thus, it can't do any work. Any force is going to speed it up or slow it down in that direction. So there's no mechanical energy once that force goes to a 90-degree angle of the displacement. So basically, carrying a heavy bucket around, even if you're moving it in the x direction, in the horizontal direction in this diagram, notice that the force is in the horizontal direction. I mean the vertical direction, while the displacement's in the horizontal direction. So for that case, we would say that the work would be equal to 0 because the cosine of this angle, cosine of 90 degrees, is also equal to 0. All right. Here's another situation. When we're picking up a box, okay, we create an upward force. We are displacing it upward, okay? The force and the displacement are in the same direction. So for this particular case, we would say the work is positive. The cosine of theta there, the cosine of the angle, they're both pointing upward. Theta equals 0 degrees in that particular case. So the work would be positive force times distance. The weight that we have to act against the box is equal and opposite to the force that we apply. We multiply that times the displacement, how high we lift the box up, and we get the amount of work done. If you, let me go back to that, by the way. If I raise the box, my work is positive. If I lower the box, my work would be negative because in that case, I'm still holding the box up, but the force of gravity is pulling it down, and also the displacement is going down. In that case, we would say the work would be negative, right? We are taking energy away from the box as we're letting it down. And in strength training, we call these negative reps. When, for instance, you lift a weight up, moving it away from the earth, that would be positive work that you're putting into it. As you let it down, however, your muscles slow its release, but you're still doing negative work on it. Anytime you have a force that is in the opposite direction of motion, that force is going to reduce the energy of the object. A great example of this is the work done by friction. Work always acts against motion. Okay? So if our frictional force points in the opposite direction that we're traveling, if friction always tries to slow things down, then it must be doing negative work. We can actually see this. Let me just erase this right here. We can actually see this in this diagram right here. We have the force pulling in the positive x direction. We have the friction, okay, pulling 180 degrees in the opposite direction. Now this is a box I'm just pushing along the tabletop. As I push it with the blue force, the frictional force in red is going to take energy away from it. All right? So if I were to do a calculation here, oops, I thought I switched to the pen. Guess I didn't. So I'm going to do a calculation here. I'm going to show you a calculation. Work equals force times cosine theta times delta x. Now here, cosine is 180 degrees. Why? Because my direction of travel is forward. The friction pushes backwards 180 degrees different. You can do this on your calculator. You take the cosine of 180 degrees, you get -1. So that reduces this equation to -1, or just negative f times delta x, where small f, is the friction. So where does this energy go to? Turning mechanical energy basically into heat. And as the box or whatever object rubs across the surface, what we tend to see is this heat is dissipated into the surface and the block. All right. You rub your hands together, you can actually experience a situation where the surface of your hands get hotter and hotter. But what had been mechanical energy that was making the box go forward now simply becomes thermal energy and heats up everything around it. Brakes, traditionally brakes in cars, are designed to create an opposing force to the movement of the wheels. This is actually a car wheel with the wheel taken off, or I should say the brake and axle with the wheel taken off. And what we can see here is this disc right there, okay, this disc right here, which is going to rotate as the wheel rotates. When you apply the brake pedal, these shoes, these brake shoes, start pinching on this disc and create friction between the surface of the brake shoe and the surface of that disc. The harder you push on your brakes, the greater that normal force between the two surfaces, the more friction that's going to be generated, and the more of your forward motion that's going to be converted into heat. Oops. Erase. So again, work doesn't happen by itself. Work comes from some type of force. There has to be energy behind that force. We need a source of energy behind that force. And again, we can think about work as being done by something, okay, in the environment on our object of interest, okay? Something's providing that energy. They're doing work on the object, either speeding it up or slowing it down on whatever object we're trying to analyze. The forces that we've taken a look at, this is important to note, are constant, okay? They're nice and easy to calculate the amount of work because you're just taking a product between the force and the displacement. Maybe we even throw a trigonometry function in there to relate the angle, but essentially, it's just a simple product to do the two. That only works if the force is constant. If it varies, we actually need calculus to do these calculations, but that's really beyond the scope of this course. Just understand that the force varies with time. It's a lot more difficult to do these calculations. Okay, let's talk about other forms of energy. Kinetic energy. Kinetic energy is the actual energy associated directly with motion. The kinetic energy of any object is equal to 1/2 the mass. This is what's surprising, times the velocity raised to the second power. It's very important to note that when we do a kinetic energy calculation, we do the v squared first, and then we multiply the different components together. Remember the order of operation. An exponent, and in this case, your exponent is 2, always has precedent over all other operations of all of other operations mathematically, other than if you have parentheses or brackets. So you square the velocity first, and then multiply it by the mass, and divide by 2, or multiply by 1/2. And that gives you the kinetic energy, okay? Kinetic energy, like mass, like speed, has no direction. And kinetic energy can increase, just like momentum will increase as velocity increases. But unlike momentum, energy is a scalar, it has no direction. Okay, there's no direction it's interested in. Nailing a hammer into a nail. The hammer is swung, we do work on the hammer. It gains kinetic energy, it has mass, it has some velocity. Again, we do work on the hammer. This work becomes kinetic energy. The hammer head flies forward, and then it makes contact with the nail. With every action, there's an equal and opposite reaction. So as the hammer pushes the nail forward, the nail pushes the hammer backward, but still, much of the hammer's kinetic energy will be converted to work to drive the nail into whatever you're nailing it into. Usually if it's wood, the nail acts like a little wedge and pushes on the fibers and pushes them apart, does work on them. Okay, let's do some other calculations. Baseball, throwing a fastball, let's say it's going around, I don't know, 90 miles per hour. How much kinetic energy does a 95 mile per hour baseball have? Well, if we do the calculations, we have 1/2. Baseball is 145 grams. We convert that to kilograms. So that's 0.145 kilograms times 40 meters per second squared. Now, again, do the square first, okay? Orders of operation. We're going to do 40 raised to the second power first, okay? Once we have that, we can multiply it by the rest. 40 squared is 1,600 meters squared per second squared. 1/2 times 0.145 kilograms gives me 0.0723 kilograms. And again, the final product is 116 joules. Sprinter with a mass of about 80 kilograms, traveling at a very elite speed of 10 meters per second. We take the 10 meters per second and square that. That's 100 meters squared, second squared. Again, the 1/2 times 40. So it's 40 times 100. That gives me a total energy, total kinetic energy of 4,000 joules. Okay. Actually, that doesn't sound like a lot when you consider, well, when you eat, a typical meal, you're taking in more than a megajoule of energy. Yet an elite sprinter will only burn off about, I shouldn't say burn off because there's inefficiencies to metabolism, digestion, and the operation of muscles, but only has 4,000 or 4 kilojoules of kinetic energy. Racehorse, much more massive, 500 kilograms, much faster speed, 20 meters per second. 1/2 of 500 gives me 250. Okay, but again, you always want to square the velocity first. So 20 meters per second squared is 400. So 250 times 400 gives me a total energy of about 1,000,000 joules. And again, compare that to an elite sprinter. Here's an elite racehorse, 100,000 joules of energy. Elite runner, 4,000 joules of energy. And again, That factor of 25 comes from the fact that the racehorses are more massive than the human being, but also because the velocity is much, much higher. Okay, so we talked about work. Oops. Work is mechanical energy added or removed from a system, so work. We've talked about kinetic energy, the actual energy of motion. When something's actually moving, it possesses energy. It possesses kinetic energy. Now we're going to talk about the last, which is stored energy. That's potential energy. But it is important to stress here that the only potential energy that we talk about is gravitation. We don't actually talk about elastic potential energy, which is a big one. Chemical energy would actually be considered to be a form of potential energy. But again, potential energy we talk about here is just gravitation. Think about the car at the top of the hill, okay? Without any other forces acting on it, if we suddenly gave it a nice little push, that car would naturally accelerate down the hill, okay, until it reached the bottom and there was no more potential energy left to extract. However, to push a car up the hill is much more difficult, okay? So when you're at the bottom of the hill, you have less potential energy. Less PE. Going to the top of the hill, you have a higher potential energy. All right. And we can extract that potential energy. Again, if you've ever been biking or running up a hill, you know that it takes so much more energy. But if you think about it, you're using energy to propel yourself forward, but you're also using energy to go to a higher and higher height, which corresponds to greater amounts of potential energy. Now again, potential energy is mass times acceleration of gravity, okay? What we knew as weight before is mass times acceleration of gravity. Work is force times distance. Here we have a force, mass times acceleration of gravity, which is our weight, times the height. So potential energy, right? Potential energy of gravity is sort of a, version of force times distance, okay? But now it's a gravitational force, okay? And the distance is simply the height at which you are at, okay? How high above sea level you are. Consider these two skiers. These two skiers are racing on a downhill jump. The one on the right weighs 500 newtons. The one on the left weighs 600 newtons, okay? Now, potential energy goes by the mass times acceleration, that's the weight, times the height. So which skier has more potential energy at the top of the hill? Well, that's really obvious. At 600 newtons, they're going to have roughly about 20% more weight, and thus 20% more potential energy at the same height than the 500 Newton racer. And again, we think about any type of winter sport. A lot of these winter sports are directly related to converting gravitational potential energy, or just simply potential energy, into kinetic energy. All right. Here's another winter sport, bobsledding. This picture, which is from the 2002 Salt Lake Olympics, Winter Olympics, it's actually quite deceiving, because in this picture, it looks like the bobsled's pretty much going on a level track. In actuality, the track starts at the top of some type of incline. It then winds its way down to the bottom, going through several turns until finally going across the finish. The camera angle makes it look again like it's pretty much flat. But without that added potential energy from the top, that potential energy being converted into kinetic energy to make this thing go, the object would soon come to a halt, basically from frictional energy, robbing it of some of its motion. Okay. Other winter sports, snowboarding, freestyle skiing, all of these downhill slaloms are converting potential energy from the top of the hill into kinetic energy, which is energy of motion. At the same time, we are losing energy from friction. Friction is doing work against the skis, okay? And this friction is slowing you down while you're converting potential energy into kinetic energy. No free ride here. What is the potential energy of a climber at the top of Mount Everest? Well, again, very simple. Take the mass times the acceleration of gravity times the height. Here we have a 70 kilogram person. Acceleration of gravity is still about 9.8, even at the tallest mountain, Mount Everest. Then we multiply it by the altitude or the height. It's 8,848 meters. Okay? That shows us at the top of this mountain, a 70 kilogram person would have an incredible amount of energy. They'd have almost 6 million joules of energy. Climbing stairs, well, a little less daunting than climbing a mountain. Oftentimes we're told to take stairs, don't take the elevator. With COVID, it's probably a wise idea. But many people actually run stairs in order to get their exercise. The reason for this is you burn much more energy going upstairs than you would running on a flat surface. So again, how much potential energy would I gain by taking a trip up from the ground floor of Carnoustus, the Arts and Science Building, roughly about 18 meters, all the way to the top if my mass was 70 kilograms? Well, take your mass, 70, multiply it by the acceleration of gravity, 9.8, and then multiply it by the height, 18 meters. Okay, we briefly touched on this idea of power. Power and energy are not the same thing, right? Power is the amount of energy, oops, wrong one. It's the amount of energy we use at any moment. So rate, okay? The two are very much related, but they're not the same thing. Energy asks how much of one type of energy was converted into another type of energy. It's measured in joules. Power asks at what rate is this energy conversion taking place? Okay? How much energy is consumed for a given amount of time? Okay? So to calculate our power, the units for power are the watt. Oh, that didn't go so well. It was supposed to be my drawing tool. And for a 100-watt light bulb, say an old-fashioned, dirty, incandescent 100-watt light bulb, that would use 100 joules every second that goes by. Okay? So if you want to use a lot of energy, you can take one of these 100-watt light bulbs, which have been pretty much phased out, leave it on for 10 hours, or take 10 of them and leave them on for 1 hour, and that will be equal to 1 kilowatt hour. Now, a kilowatt hour is basically a metric unit, okay? It's kind of strange. You know, normally when we have metric units of anything and they involve units of time, we use a second. We won't use the hour, we'll use a second. But again, it's still metric. Let's do a little calculation. And then we'll talk about another unit of power, the horsepower. Now let's consider an engine. Let's say it consumes or produces 8 million joules of work. Okay, 8 million joules of work. And it does this every minute that goes by. So obviously, we want to convert everything to SI units. The joules are already into SI units. We take the 8 million joules, 8 times 10 to the 6 joules, divided by 60 seconds. Okay? And we get that it produces 1.3 times 10 to the 5 watts of power. Probably a little more convenient to change the units here because we're dealing with such a large number, and convert upward to the kilowatt. And again, 1 kilowatt is equal to 1,000 watts. The kilowatt is pretty close to the horsepower. They're off by just a little bit. 1 horsepower, oops, that didn't work. 1 horsepower is 745.7 watts. There's a slightly smaller metric unit for horsepower, which is 735.5 watts. So you want to convert from one to the other, you either multiply or divide by 745.7. If you want to go from horsepower to watts, just multiply. If you want to go from watts to horsepower, you need to divide. And again, 1 horsepower in US customary units is 550 feet-pounds per second, or 546 watts. Typically, a small car will have about 100 horsepower. Okay, it's roughly 73.6 kilowatts of power. This is even during maximum performance. Ferrari 355 F1 engine, about 375 horsepower. Dodge Viper, although they're not in production anymore, about 450 horsepower. If you want to go to the extreme, and this happens because there's an equation, we're not going to use this very much, but there's an equation that says power is equal to force times velocity. Okay? What this means is that the force I get as the velocity gets greater and greater, the force that I get is going to be equal to the total power that the engine can put out divided by the velocity. That means the faster I go, the less force I can generate to push me forward. That's why the most extreme cars, the most extreme production car that I was able to look over is the Koenigsegg 1, which actually has a total energy power output of 1361 horsepower, 1,001 kilowatts, or roughly about 1 megawatt of power. All right. But again, typical small economy car is going to really be much beyond 100 horsepower. Okay. This particular car right here is about 13.6 times greater in terms of the overall power, because again, as this car, which is made to go very, very fast, goes faster and faster, the force that is available to increase speed, I can't get it to change the pen tool, again, is going to be equal to, let me draw there, power divided by velocity. Oh, well, let me draw up there. Don't understand that. Obviously, race car engines are going to go faster. They're going to need even more power. A typical NASCAR engine is about 750 horsepower. And, that corresponds to, little more than half a megawatt of power. Now, these engines really produce an incredible amount of power, even though they're not much bigger than the engine you might find in a light truck. And this is the reason that they have to be rebuilt just about every time after they're raced. The extreme amount of energy output that's required just does terrible things to the inside of the engine. And even after a single race, many things will actually wear out. Erase. Here's a GE90 turbofan engine, the largest jet engine ever produced, most powerful jet engine ever produced. We introduced this a little bit earlier when we were talking about force, and I'm going to bring it back here. Turbofan, the GE90 turbofan engine produces an astounding 111,000 horsepower. You want to convert that to watts? Sure. 83 million watts of power. Okay? In more practical units of energy, for that energy output, we can express the power output in megawatts. Okay, 1 megawatt equals 1,000,000 watts. That'd be 83 million watts of power. Okay, let's talk about efficiency, because efficiency is really, really important. When we look about the efficiency of something, we're looking about the overall energy that makes its way into the system. Now, some of that energy is useful. Some of this energy does exactly what we want it to. Okay? That's what we call useful energy. That's why we run these systems. We want this useful energy out. The waste energy, usually this is in the form of heat, is sent someplace else. Okay? So when we look at the overall efficiency of something, what we're trying to see is, all right, how much useful energy am I going to get for all the energy that I put in? How much is useful compared to how much I've started out with? So for instance, do a little calculation right here. Let's say my energy input is one. Come on, you're not drawing. Why aren't you drawing? There's some problems here. Oh, now the pen quit. Let's say our energy input is 1,000 joules. Okay? Now, useful energy we get out. Let's say that we get 600 joules of useful work that makes perhaps, I don't know, some vehicle go forward. Maybe it's a factory. Maybe that's a particular machine that needs that energy. Well, that means if I start out with 1,000 and I lost 600, 400 joules would have been removed in the form of heat. And when we do our calculation, and again, we want useful work, 600 joules divided by our total, 1,000 joules, we get 0.60 as a fractional part. We multiply that by 100, we get the fact that that particular engine is 60% efficient. Okay. Now, most of the time, I don't get anywhere near 60% efficiency. Most of the time, my efficiency is 50% if it's a fairly good system, especially if it involves heat. Some systems are even much less than that. A car engine, incandescent light bulb, In those cases, most of that energy, most of that waste heat, most of what I'm losing is thermal energy. Simply goes back into the environment, it's dumped back into the environment as heat. Okay? Now, years ago, there was a push to replace the typical incandescent bulb, like this one right here, with more efficient compact fluorescent bulbs. These fluorescent bulbs would have about 4 times the efficiency, so you could produce 4 times as much light for the same amount of useful energy going into them. The idea here was that the more of the incandescent bulbs that we can replace, because they're very inefficient, the incandescent bulbs generate mostly heat, the more energy that we can save and the less the carbon output would be from our country. So again, there was the push to switch to the much more efficient LED bulbs, compact fluorescent bulbs. Fluorescent bulbs were problematic in that they had mercury in them. So new higher efficiency bulbs based on light emitting diodes were used to replace them with an even higher efficiency, slightly greater in cost. But again, overall, if we do an analysis of how much it costs to replace these bulbs and how much it costs to run the bulbs, the LED bulbs, in fact, are much less expensive. The efficiency of a typical electrical generator is anywhere from 70% for a low quality generator, up to 99% for a very high efficiency generator. Electrical motors are built very similarly to generators. And in fact, in an electric car, the motor is or doubles as a generator. The efficiency of electric generators is about 50% to 95%, 93%. I think it did get up near 95%. Most gasoline internal combustion engines are only about 20 to 30% efficient, right? A large percentage of this chemical energy that starts out as gasoline is combined with oxygen from the air, okay? Anywhere from 70 to 80% of this energy simply goes out of the tailpipe and the radiator as heat. So gasoline engines are being seen as less and less viable. Hybrid engines often offer almost twice the efficiency. They do this by combining a smaller combustion engine, which is operating at its peak performance. This is coupled with a generator, which will then charge batteries, and the batteries are used to make the car go forward. Hybrid engines were preferred over electric vehicles when the battery systems were very, very small. Now today, we can actually drive cars around for hundreds of miles on a single charge. So that has changed the necessity of having a generator on board the car, less and less relevant. Now we can just plug the cars in when we need to charge them. We can travel for quite a distance. Diesel engines are more efficient than standard gasoline engines. They are able to achieve higher efficiencies because they operate with much higher compression ratios. While older diesels were much less efficient and released harmful particles to the atmosphere, newer diesels can have much better efficiency and, if they're properly designed, emit very few particles. For a long time, the hydrogen fuel cell was seen as being the best way to go forward in improving the efficiency of car engines. And this worked well for a while for experimental test vehicles. The efficiency of the hydrogen fuel cell is about 60%. So you could actually put in hydrogen-rich fuels, such as hydrocarbons in some cases. extract the hydrogen from them, and then use that to power these batteries. However, even though they have much higher efficiencies than both combustion engines and hybrid cars, hydrogen is a tricky gas to handle. Yes, it's flammable, so is gasoline. But hydrogen, first of all, it doesn't occur naturally on Earth, so you have to create it either by using electricity, and this electricity can be generated from fossil fuels, or it can be generated more directly from fossil fuels. It's also difficult because hydrogen is a gas that likes to leak out of things. So it's, your hydrogen fuel infrastructure, be it a filling station, be it the hoses that transfer the gas, or the internal gases of the engine, have to be really leak tight, because hydrogen itself leaks much more readily than just natural air. Again, with the improvement of lithium-ion batteries, electric vehicles are seeming to be the transportation mode of the future. Certainly Tesla has been very successful with this. And they are a very expensive, but actually easy way to reduce our overall carbon footprint. As you can see here, we have 3 different models on this graph. These are 3 different all-electric vehicles, okay? 2 are Tesla. You've got the Tesla Model 3, the Tesla Model X. 2 are the 2 most popular EVs outside of Tesla. That's the Chevy Bolt and the Nissan Leaf. If you look at these, their equivalent efficiency in terms of how many miles can you drive per gallon of gas. Now, obviously, electric cars don't have gas, but this makes the conversion of what the energy in the gasoline would be and how it would be derived. Here you're getting, equivalent miles per gallon, over 100 for most of these models. Now you see the Model X, because it's a slightly heavier, higher performance model, is just below 100 at 93 miles per gallon. But clearly you see that the electric vehicles outperform other modes. There in green are your all-electric vehicles, your EVs. Here in blue, you have your hybrid models at less than half the efficiency in most cases. And then at anywhere from about a quarter to about a third of the efficiency are the internal combustion engines. So clearly, quite a bit of energy can be saved or not used by switching to all EVs. Again, the biggest problem is they're so much more expensive than a simple internal combustion engine. But as lithium-ion batteries become cheaper and cheaper, we are seeing the cost of these systems come down. Lighting is also a place where we can look at efficiencies, and we can improve on these efficiencies to reduce carbon footprint. Lighting with 22% of the national consumption is just a little under a quarter of the total energy that our country uses. So if we can improve lighting efficiencies, we can, again, significantly reduce the amount of energy that we use, overall energy we use, and reduce our carbon footprint. Now, incandescent bulbs are the worst. They're about 5% efficient. And that's one of the reasons why the government has phased out all but a few of these specialized incandescent bulbs, because again, there's pushback from the current administration, but these are better heaters than they are sources of light. At 5% efficiency, that means that out of 100 joules going into the bulb, only 5 will actually make light, okay? So 95%
95% of the total energy, oops, again, I don't know why I'm having so much trouble with this pen. 95% of the total energy is simply lost as infrared light, which becomes heat. Halogen lamps, they have a better efficiency. 7% doesn't sound like much, but it's actually 40% boost in efficiency over the incandescent bulbs. However, they're also pretty much being phased out. Both incandescent bulbs and halogen bulbs get very hot. And in addition to being very inefficient, they also pose a little bit of a fire risk. Halogen bulbs are basically incandescent bulbs that have halogen gas in them. They operate at a higher temperature. The halogen gas allows them to operate hotter, and this allows them to produce more light in the visible for the amount of energy that's put in. Halogen gas allows the tungsten filament to actually regenerate itself a little bit, but they're more expensive because they require a quartz envelope. Again, fluorescent bulbs are much more efficient than incandescent bulbs. They're relatively inexpensive to make. Their biggest problem is that they contain mercury. So when they break, the mercury gets into the environment, and this can be very toxic, especially when it makes it into the water ecosystem. So fluorescents, for the most part, provided sort of a bridge due to their cost effectiveness and due to their higher efficiency, but we're replacing these with light emitting diodes, also known as LEDs. Essentially, LEDs, when they first came out, and they've been out for, oh gosh, probably over half a century. But the first LEDs were, well, half a century, would that be right? Yeah, about half a century. First LEDs were colored LEDs that were in the infrared or red. Eventually, we used different materials to get to different colors. But for a long time, a good blue LED was very, very hard to make. Again, LEDs are much more efficient than incandescent bulbs. At first, with red, yellow, and green available, we saw them replacing traffic lights. We saw them replacing turn signals. Not only were they more efficient, but they lowered the cost of maintaining traffic lights because the old incandescent bulbs would burn out over a pretty short period of time because they were pretty much on, for about at least 50% of the time. Here you're switching from red, yellow, green. I suppose the yellows would last the longest. With the LEDs, since they pretty much never burn out, I mean, you can have a problem with the power source not working, but they pretty much never burn out. That means that you don't have to go up and change the light bulbs, which means you don't have to send a crew out there and stop traffic and again, pay everybody to perform this maintenance. So that's where we saw LEDs first. But eventually, in the 1990s, they developed a white LED. Actually, they developed a blue LED first. And the way the blue LED in the white LED works is the blue LED produces a shorter wavelength of light. It shines into a phosphorus material because LEDs only produce one color of light. But the phosphorus material fluoresces and gives off all the other colors that are missing. So the blue LED is blue, of course. The red and the green, which are missing from the spectrum, are created by the phosphorescent material. And with all three colors, you get white light. Initially, the LEDs were not very efficient. The blue LEDs themselves were not efficient. The fluorescent material wasn't very efficient. But advances in these white LEDs have made them pretty much the replacement for all types of lighting. okay? Just about any type of lighting in your home. LEDs are being used to replace high intensity discharge lamps on the field. Again, they're fantastic, really, um, because of their high efficiencies, their low production of heat because they are very efficient, and also the fact that they last for a very long time. So let's compare two light sources. We'll compare an incandescent bulb, which is a 60-watt bulb, to an equivalent LED bulb that only uses 9 watts of electricity. If we use this quite a bit, we figure that the bulbs over a year are going to use, well, at 60 watts, $12.94 of electricity. At 9 watts, the LED only uses $1.94. So right there, every year that this bulb is on, operated at a typical amount, it is going to save a tremendous amount of money. Additionally, if we figure that the incandescent bulb lifetime is only 750 hours, where the LED lifespan is 25,000 hours, this bulb is used quite a bit. The LED will actually save you in replacement costs and energy efficiency about $162 over its total lifetime. So that's significant. And again, these LED bulbs can be expensive. You can get them for a few dollars a piece now. Originally, they were 10 or more dollars, but when we compare them to the lifetime savings, there's really not much comparison to be made. Okay, let's talk about machines. Machines are any type of device which can change the amount of a force or change its direction. Don't confuse engine and machine. An engine converts one type of energy, okay, could be electrical energy, could be chemical energy, as is the case for an internal combustion engine, into mechanical work, okay? The machine takes mechanical energy in the form of work and either changes what direction this mechanical work is putting a force on something or how much force it puts in. All right, for an ideal machine, the work that goes in is equal to the work that goes out. They're 100% efficient if they're ideal. For a simple machine, they're typically made of a very basic element. And as you can see, we have a few different things right here. We have a lever, which is about as simple of a machine as you can get. It's typically a rod with a fulcrum. And with a lever, we typically reduce or magnify a particular force. We have an inclined plane, which is, as its name implies, a flat surface that will reduce the amount of force necessary to go up a particular height. An incline can be something as simple as stairs. It can be a access ramp. It can be on a conveyor belt. We have a pulley, a wheel and axle, if you want to use that. A wedge is actually a double inclined plane. We can have compound pulleys, and we can have a screw, which is actually a wedge, or I guess more exactly, an inclined plane wrapped in a helical fashion. So again, nothing here is converting the energy from one type to the other. It's simply taking work in and changing either the magnitude and or the direction of the force. Here we see different classes of levers. You probably learned this at one point in your education. First class, second class, third class. Examples of these different classes you can see in our own body. The knee, for example, is a lever. Your elbow is a lever. The muscles will pull and push on the lever and allow you to move some load with them. Here's another machine. This is a compound pulley. Here you can see the advantages of this type of machine. The input here, in terms of the force, is 50 newtons, okay? But yet we're able to lift a mass of 100 newtons. How can the work in with a smaller force be the same as the work out? Well, for what you gain, you lose something. You gain a force, but the amount of distance that you need to pull on this rope is twice as much. So if I wanted to lift the load of 100 newtons, I wanted to lift that 1 meter, I'd have to pull on the string or the rope 2 meters long. So 2 meters times 50 newtons is, obviously 100 joules of work. And to raise 100 Newton mass 1 meter, that would also be 100 joules. The last thing we take a look at is energy and the environment. Okay, again, if we look at all the discussion and debate, which is on climate change, the arguments being made that we need to reduce the amount of energy consumption, thereby reducing the amount of carbon emissions, because carbon dioxide and methane are trapping energy in the Earth's atmosphere and in the Earth's oceans, basically turning our atmosphere into an insulating blanket and raising the temperatures over the globe. So again, we've already seen by improving efficiency of lighting, improving efficiency of modes of transportation, we can reduce the amount of energy we need and therefore use less fossil fuels. It's important to understand that change doesn't happen overnight. Our economy and prosperity really relies on sources of cheap, reliable energy. And although it'd be nice to switch all green at once, we don't have the infrastructure to do that yet. Most of our energy, even with all the solar panels going up and all the wind farms going up, they still account for a very small fraction of the total energy that we use to power our economy. So turning off fossil fuels would be an economic disaster for us. But what we're seeing is more and more green technology infrastructure being built, and thus the reliance on carbon dioxide producing energies is decreasing. And again, here's a look at a snapshot of our fuel consumption. At the current rate, we will only increase the amount of petroleum that we burn. Natural gas is a little bit better, but you can see coal makes a pretty good percentage still. But all three of the top sources of energy still remain fossil types of energy. Nuclear and renewables are still a minor fraction of the total that we consume. Now, the greenhouse effect, which basically is responsible for climate change, is both a good thing and a bad thing. First of all, without it, we don't exist. Without the greenhouse effect, our planet would quickly freeze over and life would be nearly impossible, if not, in the best case scenario, very, very difficult. But what's taking place here is the normal greenhouse effect that has kept our planet a fairly constant temperature is being enhanced by the additional carbon dioxide that we're releasing. And as it does that, it traps energy into the Earth's atmosphere by essentially blocking the infrared light, which would otherwise radiate out into space. Now, there's a lot of debate in politics about this, but the science is fairly clear. If we look at the effect of different components of what carbon dioxide does to the atmosphere, we will see that greenhouse gases, carbon dioxide, has the greatest impact. This is called radiative forcing. It's how much it impacts the rise in temperatures in the atmosphere by blocking the infrared light. You can see methane is also starting to play a bigger and bigger role too. Even ozone in the troposphere where we live, which is due to pollution, due to internal combustion engines, plays a significant role. And as the atmosphere gets warmer and warmer, we're actually putting water vapor into the stratosphere. So looking at the net effect of burning carbon-rich fuels, we see there's a warming. As temperatures get up, there's actually a reverse feedback. Clouds become more and more prevalent. They block some of the visible light coming down. Other aerosols due to pollution also create a blocking effect. You might have noticed that it was a little bit cool about the time that the aerosols from the smoke in the West came into our area. So pollution will have that particular effect. But again, the overall impact is what we call the net anthropogenic component. What we're doing is that we are heating up the Earth's climate by burning fossil fuels. Okay? Now, not all fossil fuels are equal. Greenhouse gases are produced more readily by dirtier fuels like coal and less by cleaner fuels such as natural gas, which contains mostly methane. Now, again, politics aside, you can see that the United States, although we only have 4% of the Earth's population, we have roughly a quarter of the total greenhouse emissions. So, if we can work with other places such as Europe, right now, China has surpassed us. This is done in 1995. I should really update this because China's surpassed us in greenhouse emissions. We're still around 25%. And again, these are the, basically looking at the amount of greenhouse gases in the atmosphere. If we look at carbon dioxide emissions and we match it with the global temperature anomalies, which is a fancy way of saying how much warmer than average it's becoming, you can see a very nice connection between the two, okay? As we dump more carbon dioxide into the atmosphere, clearly our temperatures have gone up. So this connection has been pretty well established. And the worst part about this is the greatest anomalies actually occur in the Arctic and the Antarctic. And that has a double effect. If you're heating up the Arctic, the impact that it has, oops, why did I keep jumping to the next slide? The impact that it has is it melts a lot of the permanent snow and the permafrost, melts the sea ice, and that makes the Earth actually absorb more energy. In addition, by melting the permafrost, there's methane trapped beneath this permafrost. It's built up from the decay of organic matter beneath that. And methane is a pretty potent greenhouse gas. So, sources of energy. Wood was one of the original sources that humans used as a source of energy, primarily used for heat and cooking. Not a great source of energy these days. For most cases, for most of the population, only produces 15 million joules per kilogram. And while we can use wood in some areas to heat homes, um, basically, if our forests are well maintained by cutting out the less healthy trees, it'll actually enhance the forest growth. But this could never be used as a primary source of energy. Um, to use it as a even significant source of energy, we deforest the surface of the earth, and that would add more carbon dioxide. So, fine for rural areas where it's used as a supplementary source of energy, but for the most part, it's a archaic source of energy that can't really power our economy. The Industrial Revolution saw us switching to coal. Coal is much more energy dense at 30 to 33 million joules per kilogram. The problem is when we burn coal, it's highly pollutive. It produces the emission of heavy metals, it produces large amounts of carbon dioxide. And although more modern plants do scrub many of the pollutants out of the stack, this actually just makes the coal plants more expensive. And currently, not only are the a greenhouse disaster, they're highly inefficient as a source of energy and very expensive. So even if regulations um, allow more coal plants to be built, the cost of coal is just making them, well, a technology that nobody wants anymore. Coal's carbon footprints are very significant. Approximately 1 kilogram of carbon dioxide is released for every kilowatt hour of energy we extract from coal. Um, Lignite coal, which is sometimes called brown coal, is um, a little bit more pollutive, and anthracite coal is actually the most pollutive. Bituminous, almost about a kilogram of carbon dioxide per kilowatt hour produced. And again, coal plants really have to struggle to filter out their pollutants. Burning coal produces soot and dust, produces mercury, releases lead, arsenic, chromium, nickel, cadmium. All these elements which have been trapped within the coal, which is actually, um, coal is actually ancient forests, which have been buried and basically fossilized. And of course, sulfur dioxide, nitrogen oxides, and ozone are all different pollutants. Later on, petroleum was seen as a source of energy, more energy dense than coal at 44 to 48 million joules per kilogram. Crude oil is made out of a thick black liquid that contains many different types of hydrocarbons from decayed plant and animal life, which had lived in the ancient oceans. So forests produce coal. Um, Plankton from the oceans was our source of oil. Petroleum is cleaner than coal and produces less carbon dioxide per joule of energy. However, petroleum is still a huge contributor to carbon dioxide. Its carbon footprint's better. It's 0.880 kilograms as opposed to 1 kilogram for every kilowatt hour of energy. But unfortunately, this isn't really uh, enough of an improvement to make things better for climate change. The other problem is obtaining petroleum oil has become more difficult, more energy intense. Extracting coal from tar sands, I'm sorry, extracting oil from tar sands or bituminous sands or bitumen um, is very controversial because it takes just about as much of a carbon footprint to get the same amount of energy out of this type of oil, shale oil, as it does out of coal. So, when you hear about the pipelines being built from the tar sands in Canada and the bitumen sources, these are highly polluting sources. Natural gas, 56 million joules per kilogram. Natural gas of all the fossil fuels is actually the best. It's mostly methane. And like coal and petroleum, it's from fossils which have decayed. And burning natural gas has a lower carbon footprint, about 60% of carbon footprint that we find in coal. What would I estimate the percentage? Well, let's say probably about 70% of the carbon footprint of oil. So it's significantly better. There's a lot of controversy associated with hydraulic fracturing, which has been used to produce natural gas, but certainly the amount of polluting associated with fracking, believe it or not, is much less than what we get from coal and oil. Fracking is a new technology, so it's still a technology that needs to be better studied and regulated. But again, in terms of carbon footprint, it's an improvement over what we've seen with coal. And again, basically the way that this works is they'll pump a hydraulic, fluid, hydraulic, water and detergents into the ground. This will fracture the rock because it's done at very high pressures. They also put sand in there to basically act like wedges to keep the fractures open. And then the gas comes back through the opening that's drilled. So again, currently fossil fuels make up a very large percentage of the total energy that we use. We're beginning to supplement some of these fossil fuels with other fuels such as biofuels. Ethanol was one of the longest standing biofuels that we've had. It creates ethanol by fermenting corn. So ethanol is considered to be a renewable. It says methanol. It's not methanol. It's ethanol. It's 2 carbons source. But it, even though it doesn't really contribute to the acid rain problem, it's not a direct impact with the greenhouse because you're using photosynthesis to create this fuel. The operation of machinery and the energy intense nature of fertilizing corn, especially in this country, means 2 things. One, you're reducing the amount of food that is available, but also 2, you are burning fossil fuels in order to generate the fertilizer. So ethanol really doesn't give us the gains that we think that the biofuel would give us. In comparison, gasoline is still bigger in terms of footprint, but corn ethanol doesn't give us the reduction that we want. Still only about 19% reduction. You see the averages here shown in green, and it's a little bit hard to figure out what they're trying to say here. Here's the current average. Here's using natural gas to create the fertilizer and operate the machinery. And then here's using biomass, burning the waste to generate the fuel necessary to create the ethanol. Okay, that's not to say that ethanol isn't a good source of biofuel if it's done correctly. Here we see ethanol being created using sugarcane. This is very popular down in South America. And, if done properly, if you're not destroying ecosystems doing this, you can very efficiently convert sugarcane, which, as you know, has a tremendous amount of sugar in it, into ethanol. Whereas corn, you've got to take the starch and use enzymes to break the starch into sugars before you can ferment it. Our hope is that someday we can take waste plant, what we call cellulosic biomass, waste plants, and use enzymes to break down the ligand and the cellulose into sugars and then ferment that. That would create a very good, almost carbon neutral source of energy. But again, that's still something that is off in the future. So again, here's generating ethanol fuel from different sources. Sugarcane is, oops, let me do something. I'll use the other tool here. Sugarcane right now represents the most efficient way to do it because there are no enzymes involved. You can directly ferment the sugars into ethanol. Corn, not so good because we need enzymes to break down the starch. Alpha amylase, glucoamylase are enzymes that take energy to do this. Oops, my poor pen fell apart. That's a bummer. Okay, there it goes. Biomass would be the ultimate source because you're not taking away from food. You just take waste plants. Anything from grass clippings to you could grow grass in marginal agricultural land. But again, this is something we don't quite have the technology for yet to do cheaply. We have to pre-treat the cellulose and then convert that into a sugar. So basically, it's a double process. You'd have to break it into a starch-like substance and then into a sugar. There are biofuels that do have a small carbon footprint. Biodiesel is supposed to be much better than other sources, and you can see the carbon footprint of different biodiesels that are created from rapeseed, which is similar to sunflower seeds, and also from soybeans. Again, the future could have us take pond scum and turn that into biodiesel. This again is another holy grail of biofuels. We could grow the algae, have it produce these large lipids, and then treat it and turn it into biofuel. Initially, this looked very, very promising because algae grows very quickly. It's found all over the place. It's found in very poor conditions. It could even be used to pull the nitrogen out of fertilized water from cropland runoff. But again, this technology is sort of stalled to extract an inexpensive biofuel from it. And again, if we could create this, you can see the much lower carbon footprint for biodiesel made out of pond scum, well, algae. Hydrogen, again, is kind of sort of a renewable source of energy. It would be if it came directly from water. However, hydrogen takes energy to create. And we could use nuclear fusion as an economical way of generating hydrogen. Believe it or not, the Fukushima nuclear disaster showed explosions. These were not nuclear explosions. Explosions at the power plant were created when natural nuclear effects were breaking the water down into hydrogen and oxygen. But again, this still is an expensive technology and has only been seen on a limited scale. Quite frankly, hydrogen is probably going to not come to fruition, less because of its difficulty in technology. It's probably going to have a bigger problem coming to bear because lithium ion batteries are just able to store energy so efficiently. Of course, solar energy, we're seeing more and more of it. Solar energy over the lifespan of a solar panel, because it takes energy to produce solar panels, is currently at about 1/10 of a kilogram of CO2 per kilowatt hour produced. However, as more solar panels come online, this number will continue to decrease. And of course, if we had a solar grid where the solar panels were produced all by solar energy, that number would become very, very small indeed. Be a self-regeneration type of effect. Wind, even lower, 2 1/100ths of a kilogram of CO2 per kilowatt hour. But of course, they've got to be placed at the right location. Geothermal, yeah, a little bit more than the other two, but very easy infrastructure if it's available. You've also have geothermal at home. This is a way of actually improving your efficiency at home, where to heat and cool your house, you drill into the ground and you dump heat there during the summertime because it's easier to dump heat because the ground is always 50 degrees, and then take up heat during the wintertime using something called a heat pump. Again, this would increase the efficiency of your overall heating and cooling system and thus reduce your carbon footprint. Hydroelectric, pretty much we don't like hydroelectric anymore, even though the carbon footprint is small. The primary reason is because hydroelectric damages the river ecology very, very badly. Although we can get low carbon footprint energy from it, the damage to ecosystems is quite large. So good carbon footprint, bad eco footprint. Believe it or not, nuclear fission is, although a very expensive technology, actually a very safe technology in comparison to fossil fuels. We only see the very big accidents that have happened, such as Chernobyl and the Fukushima accidents, which were caused by human error. However, if nuclear fission is operated properly, it is a very clean type of energy. Yes, you have to eventually bury the fuel in the end, but unlike solar and wind, which depends on the weather, at this point only makes up a very small percentage of our energy grid. Fission can produce a very good base load and is currently a technology that we use quite a bit. Fusion is supposed to be the ultimate source of energy in the future. However, fusion always seems to be a decade off. Fusion reactors do not melt down, and their primary source of energy comes from water. However, again, we still have yet to build a power plant that is, cost effective. Still very inexpensive technology. Going way into the future, the ultimate technology would be a black hole, believe it or not. We could convert up to 90% of the energy contained in matter's mass into usable energy using a black hole. But if you know anything about science or science fiction, not the kind of thing you want to have sitting around. So again, looking at the problem of climate change, if we want to prevent our climate from continuing to get warmer at an ever increasing rate. It's climbing exponentially. We need to reduce the amount of energy that we get from carbon sources. Although going after the source of the energy is a good way of doing this, a better way is actually conservation. If we can reduce the overall energy need that we get, that also reduces how much of a reliance we have on fossil fuels. Even what you eat has an impact on how much carbon footprint you have. Beef is oftentimes criticized as being having a very high carbon footprint in order to produce. So if you eat a tremendous amount of beef, and especially the lamb, you have a large impact on the greenhouse gas emissions just from what you eat. As you go down the scale, you see, well, if you eat turkey and chicken, it's a little bit better. But only when you get below the animal sources of protein down here, you start seeing like potatoes, peanut butter, yogurt. Well, that comes from dairy, so we got to be a little careful there. And again, rice, nuts, broccoli. You like tomatoes? Very low carbon footprint on that. So I'm not a vegetarian. I'll admit it. I like I like my animal protein as much as anybody. But one of the arguments being made is, vegetarians have a much lower carbon footprint because the energy needed to produce these different foods is highly different. Again, changing your lighting. LEDs have reduced the amount of energy that we use to create light. If you're still using incandescent bulbs, you need to switch them out. In fact, your power company will even pay you to switch them out. Transportation. Okay, transportation. When we compare different types of transportation, cars are very, very inefficient, have a large greenhouse impact. Taking mass transportation by rail, by bus, greatly reduces the overall impact. Okay? I live 80 miles away, so I'm not cycling. I do have an electric car, but right. Oops, there goes my pen. And again, you can just look at the kilograms of carbon dioxide produced heating your house by different sources of energy. And obviously, electricity is the worst way to heat your home. Natural gas, as we said, that's carbon footprint's a bit better. And using a heat pump, using geothermal does do a long way to reduce your carbon footprint. I actually switched to pellets. Okay, I used to chop my own wood and cut down dead trees in my forests because we live on a farm. But I've switched to biomass pellets, and they are I like them because they have a lower carbon footprint, although they're not saving me a lot of money. My original energy when we bought my house was a fuel oil boiler, so clearly about 10 times the carbon footprint for the same amount of heat. Okay, well, that's it. I am going to stop the recording.